Let's move to the third aspect of pre-analysis, hand calculations of expected results and trends. So we now know what's a mathematical model we want to solve. We've talked about the numerical solution strategy that ANSYS will use. We will look at post-processing and ANSYS, so let's move our attention to hand calculations. And in this particular case, this mathematical model that we have has an exact solution. So we have an exact solution. We can solve the mathematical model exactly, and we can compare our numerical results to that exact solution of the same mathematical model. Before I talk about the analytical solution, let's think about the trends. Okay, so I'm going to think about trends, and in most problems you're not going to have an analytical solution, which is why you're turning to ANSYS and the numerical solution technique. But you can always think about the trends, and that's going to be your hypothesis of what's going to come out of the solution. That's very important to do. One thing we can work out is what is the direction of the heat flow at the boundaries. And you can do this for any heat transfer problem. And in our case, the BO number is 5. We have W equal to 1 and K equal to 1. So essentially, we are setting the convection coefficient to be H to be 5. And you're going to get, significant convection between the block and the fluid. When I present this in class at Cornell, I ask students to take a few minutes and work out, the direction of the heat flow at the boundaries. And I'll give you a clue. The heat flow in any direction is proportional to the temperature gradient in that direction. If I come to this boundary, there's no temperature gradient in the x direction, so I can't have any heat flow in that direction. Okay, so Qx has to be 0. Using that clue, you can work out what is the temperature, whether you can have heat flow in that direction, tangential direction, and the normal direction at each of these boundaries. And you can confirm your hypothesis from what you get in ANSYS. So at this point, you might want to pause the video and kind of sketch that out on a piece of paper. And the analytical solution to our mathematical model, I'll show you, and this is courtesy Professor Michel Louge, who presents this in his class when he teaches the heat transfer course in mechanical engineering at Cornell. The analytical solution is found using separation of variables, and it comes out to be in the form of an infinite series. And this is a constant, okay? So these are constants that depend on these eigenvalues, and in a moment I'll indicate how you find those eigenvalues. And it's going to depend on the BO number, and it's going to depend on the aspect ratio. And the BO number and the aspect ratio are inputs into the problem. And these functions are eigensolutions, and they have a cosine variation in the x direction, and then they have this kind of variation in the y direction. So it's a product of the x variation and the y variation. And the eigenvalues satisfy this nonlinear so-called transcendental equation. And the textbook that is used at Cornell, and this is probably true of other heat transfer textbooks, they tabulate the values of lambdas for different values of the BI. So you can find the lambdas, then you can find theta at, say, you want to find the temperature at any x and y. So you have x and y, so you can find theta, you can find f, but you have to do this for each eigenvalue. And then you have to sum over the series, and you would use kind of a finite number of terms. This is a relatively simple problem. In fact, for somebody who knows ANSYS, this problem is a piece of cake. And the analytical solution is fairly complicated, and then it has restrictions on the boundary conditions and also on the geometry, because you can't extend it to any geometric shape. Whereas the ANSYS solution methodology is not restricted by the geometry shape or by boundary conditions. So that kind of gives you an idea of the power of having a tool like ANSYS at your disposal.